on the line. So I'm going to be able to create that vector pretty easily, don't you think? I have 2 points. I can always create a vector between them. And this is which one? The A or the B? This is the A, okay? And then I need another vector which goes from any point on this line to that point. And so how about this one? That okay with you if I do this one? That's B. And once I know what those two vectors are, I'm going to cross them, take their magnitude, and divide by the length of A, and I'm done. That numerical answer is the shortest distance between that point and that line. All right, so what is the vector A, just so I have it here? -4, 6, 5. And what's the vector B? 3, 3, -12. Now, should I do A cross B or B cross A? Is it going to matter? Because you're going to take the magnitude of it. I know that when you cross them, the order does matter, but once you take the magnitude, it no longer matters. Okay? So that's it. We're there. I'm going to compute the distance to be A cross B over magnitude of A. Now, the bottom has to be magnitude of A. It cannot be magnitude of B. It has to be A. And A is always on the line. All right? So let's get a cross product here. And I'm going to leave this right now as a magnitude. What's the cross product of A and B? It's a vector, right? Negative, what did you say? -3. Is that right? Hold on. We're doing a cross product, right? So I'm covering up these two. Should be negative. Okay. So what's the first component of the cross product? -87? -87. And then to get the middle one, I've got 48, take away 15. I can't do that. What is that? Negative 33. And then the last one is negative 30. Magnitude over the magnitude of A, which means I'm going to need to do the square root of 16 plus 36 plus 25. That one I can kind of just see it and put the components and square them. I have not taken this magnitude yet. That's my next line. Y'all see it all though? Any questions? All right, so now we have square root 87 squared plus negative 33 squared is the same as 33 squared.
Why is it
plus,
negative 33 again?
I don't know. I was told it was negative 33. Let's check it. That's 48, and then you take away 15, which is 33. But remember, the middle component, you change the sign. Yeah. And then the last one being 30, it was -12 minus 18. Yeah. So all of this over whatever this is, and I'll wait for a volunteer for an answer on that.
97.76.
About 97.76. Anybody else get that?
Round to the 7.
Round to the 7? Okay. It's fine.
Like 97.77.
That's
That's right.
What I ended up getting was that, but I only did that for the top, so I divided by the square root of 77 on the bottom.
So this is without the square root of 77 on the bottom yet?
Yeah.
Oh, okay. So this is over root 77 still? Okay.
And then that is equal to 11.14.
11.14. Yeah? This stuff is just arithmetic, so you can do that, I hope. Pretty cool. Questions? That's it. Where's the homework assignment? I don't see the homework assignment. I guess I'm going to have to send that to you. You should now be able to complete the mini exam. The mini exam, that last one is asking for what? What does the question say again?
Center of the sphere.
Find a distance, or?
It's the center of the sphere, and then there's a plane with a. Find the vector equation of the line.
Oh, find the vector equation of a line.
It passes through the center of the sphere.
Passes through the center of a sphere, and
Point of intersection of the line.
point of intersection of a, or line of intersection.
It's like a line in the plane. And you
A line in the
find point of
plane.
intersection.
Oh, okay.
And then there's a point at the center of the sphere, and a line equation from there to there.
Oh, you know what? You don't even need those distance formulas for that. Yeah. You want to find the vector equation of a line, right? What do you need for the vector equation of a line? Direction vector and a point, right? One of those points is the center of a sphere. So you can find the center of a sphere if they give you the equation, which I do. And then you need a direction vector. So you need the vector that goes from that point to that point of intersection. How do you find the intersection of a line and a plane? Plane, line. How do you find that point of intersection? I don't know. It has to be an XYZ that satisfies both, right? Okay. See how you do. You've got till Monday to figure it out. I've had only a few people ask for help, so that's okay with me if y'all are okay, you know. But please don't be like after you get the grade back and it's like a very poor grade. Don't be like, well, I was having trouble and I really didn't know where to start, because I'm just saying, I don't know. I kept on telling y'all, like, ask for help.
With number 6, do you want us to like restrict the equation of the line to those 2 points? Or you just want it infinity?
Yeah, just the line that goes through those 2 points. So you don't have to do a restriction on t. All right, we're moving on. 11.6. I'm going to have to send you the homework assignment for this section. All right, 11.6 is 10.6. Thank you. 10.6 is a section that we really could spend a lot of time in this section, but because of technology these days, we can go a little faster. There are a few elements of this that we'll look at that'll be important later, but the big idea here is that you need to become familiar with equations and what they draw. So like if I put y equals x squared up here right now, everyone should be comfortable with the fact that that's a parabola, right? If I put y equals mx plus b, everyone should know that that's a good old-fashioned line in 2-dimensional space. Well, now we're going to be working in 3-dimensional space, and there are some common equations that we need to be familiar with so that when we see them, we know what they draw, all right? And there's a bunch of them. So let's go ahead and get started. We are now talking about cylinders and what are called quadratic surfaces. I'm going to kill one of these lights so that we have you can see a little better, because these pictures are going to get kind of detailed. And we will start now with some 2-dimensional stuff. So remember the conic sections in 2-dimensional space. A circle, and trust me, don't try and copy everything I'm putting down here, right? Don't try and write everything, because you're not going to be able to keep up, all right? The standard equation for a circle, x squared plus y squared is r squared. There, the circle is centered at the origin, right? That's the standard formula for it. Circle, yay. All right, move on. Now, ellipses. The standard equation of an ellipse, x squared over a squared plus y squared over b squared equals 1. What if a squared and b squared are the same number? It's a circle. Do y'all see that? Like let's just say that this was r squared and r squared. Then you can multiply both sides by r squared and you would have x squared plus y squared is r squared. So a circle is a very special case of an ellipse. An ellipse is more general. So if we change the A, B, and C, or sorry, the A and B, it changes the shape of our ellipse, right? So the things to point out here, we have our variables are always squared in an ellipse and in a circle. We have addition between them, right? We're dividing by these constants squared, and it's equal to 1. That's the characteristic of circles and ellipses. Squared variables added together, right? You'll see why I'm saying that in a moment. How about this one? Hyperbolas. Here's what they look like. You can adjust the A, B, or the A and B on this also. But look at the format of a hyperbola. Looks a lot like the ellipse, right? Only difference? Sign in between them is subtraction. Okay? Also, if you imagine there's kind of like this symmetry right here between the two, and you've got like these two parabolic looking things that go away from this, right? This we would look at as being the y, like something that's parallel to the y-axis, right? And notice that the subtraction is on the y. If we were to reverse this and put a minus here and a plus here, this picture would go like this instead. Okay, so if you had minus x squared over a squared plus y squared over b squared equals 1, then it would look more like that than this. Right? Those are the slight little differences you should see in those. Hyperbolas. All right, and now we'll move into three-dimensional space. So, in three-dimensional space, we have equations involving x, y, and z. And you don't actually have to have them all there to get something, to get a surface. So you can still have a surface in three-dimensional space with only 2 of the 3 variables appearing, or even 1. Before computers and 3D imaging, mathematicians had to try and graph them by hand. To do this, they would determine what are called the traces of the surfaces. Traces are the curves created when you intersect the surface with planes which are parallel to the xy plane, xz plane, and yz plane. I'll explain that in an example. And after we do one, you're going to be like, wow, that's really a pain in the ass. All right. So, cylinders. That's what we're going to talk about right now, cylinders. So what does a cylinder look like? In your mind, what is a cylinder? Like a can, right? Beer can. You brought up beer. I didn't bring up beer. It's like a beer can, right? Like this. But it extends forever, right? Vertically, it extends forever. And it's hollow on the inside, right? It's not a solid rod. It's actually hollow inside. And you could almost look at this as being like an axis that goes through the center of it. And if I draw it this way, it would almost give the appearance that it opens along the z-axis, right? Or because it's three-dimensional, z has always been up and down for us. This would be like, here's your z-axis. This cylinder appears to open up through the z-axis. But I could also have a cylinder, let me draw three-dimensional space here. I could also have a cylinder that is more like along the x-axis, right? Or I could have a cylinder that goes along the y-axis. Or I could have that cylinder that is along the z-axis. So when it comes to cylinders, we have different orientations we could have them in. And then you could have a cylinder that's like kind of just pointed anywhere, right? We're going to be looking at just these 3 different types. All right? We're not going to go to arbitrary. That gets really tough. But the main thing about the idea behind this traces thing is this. It says here that for cylinders, traces are circles and lines. So I want you to imagine if I were to come in here with my magic sword here and slice through this thing like this, right? And cut through that cylinder, then where I cut through it, what would I create? What would that image be? I would create a circle where I cut through, right? And no matter where I cut it, right? Cut here, cut here. Now these cuts have to be orthogonal to this axis, all right? So if I cut through with orthogonal cuts, I'm going to create circles no matter where I cut it, right? Those are called traces. They're traces. Now, it also says that traces are also lines. So that would mean if I come through here and this time, instead of cutting through this way, I turn 90 degrees and I cut through like this, then what am I going to get? Where I actually hit the cylinder, I'm going to create a line. I'll do that in green. I'm going to create a line. And then I'm also going to create a line as I come out through the other side, the back side of the can, right? I'm going to actually have a line there. Do y'all see them? So I came through, I cut like this, I got circles, cut like this, I got lines, and then what if I cut through like this? So what I'm trying to get at is I've come in this way, right? But what about like this way? Cut through. What am I going to get? I'm going to get lines again, right? So I'm going to be taking that can, I'm going to be coming in, cutting it like this, and then when I cut down, I'm going to get the line down the can. Same on the back side. So that's the way we kind of define cylinders. Cylinders are objects that when you cut them, when you have these traces, you get circles and lines.
Would it be kind of more accurate to say ellipses? Because like, let's say you, instead of, straight up and down.
But no, the cut has to be perpendicular to the axis. So if you come in at an angle, then you're going to get ellipses. But all of our cuts are going to be parallel to the coordinate planes. So this cut would be parallel to the XY plane. This cut would be parallel to the XZ plane. And then this cut right here would be parallel to the YZ plane. Whoa. This is basically everything I just did, but it's too big to look at, so let's zoom this out. So this is me cutting through the can with planes. So I'm slicing through with planes, and do you see the blue is all the lines? Those are lines. And then I can cut through from the other direction, and you see that I'm getting lines also. And then I can cut through with planes that are parallel to the XY plane, and you can see all those cuts give me circles. So circles and lines are what you get when you draw cylinders, when you cut them up. Next, geometry, or I should probably write the equation, right? I should have the equation here. We're going to skip that. We're not going to do that by hand. If we change the variables, I'm missing the equation. Where is it? It's got to, oh, there it is. Ah, okay. I was looking for the equation. I was like, I know it's got to be here. Here's the equation of that cylinder. Does this look familiar? X squared plus y squared equals c squared.
Yeah, it's a circle.
It's a circle, right? Except now we're in three-dimensional space. So there's no z in here, is there?
No.
So z is what we call free. It's a free variable. So it's like you're drawing a circle of radius c, and then you're allowed to let z be whatever you want, so you can move it up and down, and that draws the entire cylinder. Make sense? The free variable on a cylinder is the axis that it extends out, of, all right? If we change the equation and change our free variable, so if you have an equation x squared plus z squared is c squared, where y is free, then your cylinder is going to go out the y-axis. You're still going to get circles and lines as traces, as cuts. And then finally, if we change it and get rid of the x, and you have y squared plus z squared is c squared, then you get that cylinder coming out the x-axis.
C is represented with the circumference of the...
C is the radius of the circle. C is what we had as radius earlier, but I'm not calling it radius. I'm just calling it C. So that would be the radius of that circle right here. You're just drawing a bunch of circles and just moving them along the x-axis. All right, now the next type, parabolic cylinders. The traces are parabolas and lines. So I don't know if you can imagine what this looks like in your mind, but when you cut it, you're either going to get parabolas or lines. So let's look at it now. A parabolic cylinder. Take all these things out of here. This is a parabolic cylinder. Check it out. From one side, what does it look like? It looks like a parabola, doesn't it? That kind of look like a parabola to you? But then, you know, you kind of tilt it around. It's just like a folded up sheet of paper, right? It's like a sheet of paper, you just curved it. And the sheet extends in both directions. So let's try cutting this thing up. There are trace curves right there. And let me actually show the plane that cuts these. So that plane, see that plane cutting it? The green plane cuts it there. And that forms a parabola, doesn't it? And then if I try and cut it with this plane, I'm getting those blue lines, right? Right here. And what about if I cut it vertically? And let me take the other ones out of there so you don't have to see them. There's my vertical cuts. Man, those are hard to see, aren't they? But it creates lines also. Now, from looking at this, can you tell from this little like taco shell looking thing, which axis is this taco shell thing opening out? This is opening out the y-axis. The parabola, you know, starts out kind of like on the origin and goes up like in the z-axis, but I'm talking about which way does that thing extend? This thing comes out kind of like the cylinder was earlier, goes out that way. That looks like it's along the y-axis, right? Okay, let's look at the equation of this. Here's the equation of a parabolic cylinder. Z equals a constant times x squared. What's the difference between this and the cylinder equation? What's one difference?
One is secondly used.
Yeah, you have, okay, so with cylinders, we had two variables and then one of them was free, right? And the two variables we had, both of them were squared, weren't they? And added together. Here, you have one variable that's free. You have two variables here, but only one of them is squared. The other one is not squared. And that's what can help tip you off to what you're looking at. This looks like a parabola, right? This looks like the good old-fashioned y equals x squared, but we're in three-dimensional space, so it's going to be extended out. C just changes how it opens up, like if it's opening up real wide or real narrow. All right, now we can change the variables. Okay, so now if your equation is, where is it? Z equals cy squared. So if the x is missing, then it's going to open out the x-axis. And then what if the z is missing? It should go up and down, right? I thought I had a picture of that. Yeah, there we go. So if your z is free, that's what it will look like. And here's what I meant by changing the value of c. Change the value of c, it could flip your taco shell the other way. All right? Make it wider. Oh, too wide. There we go. All right. Parabolic cylinders. Ellipsoids. Traces, all traces are ellipses. All traces are ellipses. No matter how you cut it, this way, right? No matter which way you come in, you're going to get an ellipse. So it looks like an egg. The shell of an egg.
Am I
An M&M? Yeah. Sounds good. So you see these cuts here? I've got these cuts here. Where is it? Uh-oh. Oh, yeah, that's right. I remember this really caused some problems. My code. There we go. So see, I'm cutting it here. And everywhere I cut it, I'm getting ellipses. Now, what is the equation of an ellipsoid? There it is. Isn't that basically the same as the equation of an ellipse? With what one thing added? Z squared over c squared. So ellipses have all three variables appearing, right? All of them are squared. All of them are being divided by some numbers, added up and equaling 1. So this looks a lot like an ellipse, the equation of an ellipse. All right, let's move on to the next one. Elliptic paraboloid. Whoa. So you cut this in opens in the direction of the variable raised to first power. Let's see. Traces are ellipses and parabolas. So when you cut it certain ways, you get ellipses. Cut it other ways, you're getting parabolas. What the heck does that look like? Oh, it looks like that. Looks like a bowl. So look, do you see these cuts? All those are parabolas, aren't they? Okay, so how about if I cut it? Get out of there. There we go. What if I cut it this way? Right? I'm getting ellipses there. Now, they do look like circles, right? But if you kind of pull it out like that, you can see that those are ellipses. Okay? So, ellipses this way. And what about this way here? There. So I'm cutting through this way. What am I getting in that direction? Parabolas, right? If I turn it to the side, I've got a bunch of parabolas. You see why they call this an elliptic paraboloid?
It's basically an ellipsoid cut in half.
Yeah, ellipsoid cut in half, where you don't have that top cap, right? So it just extends forever. All right, what does the equation look like? Whoa, wasn't expecting that. You've got x squared, right? All three variables appear, but only two of them are squared, the other one isn't. And notice that the variable that has the power 1 on it corresponds to the axis, the direction in which the paraboloid, the elliptic paraboloid is opening up. So would you agree that this thing goes like kind of up the z-axis? That's the variable that was to the first power. I don't expect that you're going to memorize all these, okay? We need to notice some of the characteristics, all right? What is this? Maybe you can tell me what that is just by looking at it. Is that still an elliptic paraboloid?
Yes.
Yes, we've got all three variables appearing. Two of them are squared. The other one is to the first power, right? So this should open out the y-axis. That's what it does. Here's the same thing. Two of the variables squared. Third variable is not. This should open out the x-axis.
So x over c was
Some constant. Yeah.
was over to the negative power, it would reach the other way?
Yes.
Okay.
If c was negative, we would go out the other direction. Hyperbolic paraboloids. So we're going to get hyperbolas and parabolas when we cut them. What? Oh, that's what you meant. Sure. You take that stuff out of there. Take that out of there. All right. This is what it looks like.
Interesting.
It's weird looking, huh?
It's like a valley.
So if we cut it here with XY planes, like come in, slice it up. Right, do y'all see those XY planes? They're parallel to the XY. We cut those and we're getting hyperbolas, and you can see that if you look at it from the top, you can see all the little hyperbolas we're getting. If we cut it from another direction, let's see. Get this out of here. There we go. I don't know if you can see those cuts coming down like this. And we turn that from to the side, and you can see all the little parabolas we're getting. Hyperbolic paraboloid. What is the equation of this? Hey, that looks familiar, doesn't it? That's almost the formula we just had. But we've got a subtraction between them instead of addition. That small little change creates a huge change in what the picture is. And then, of course, we could change the variable again and, you know, have it kind of open in a different direction. All right, a cone. Traces are ellipses and hyperbolas. There's your cone. You cut it this way, you're going to get ellipses, or hyperbolas, sorry. And if we cut it this way, we're going to get, ellipses. Hyperbolas and ellipses. Equation of a cone. All three variables appear. All three of them are squared. Two of them are being added. The other one's on the other side, right? What's going to happen is eventually we're going to just like give you an equation. You're going to have to kind of manipulate it and turn it into one of these and then say what it is. Yeah. Yeah, well, it won't be that bad. All right, cones. So here's just cones opening up different axes. Hyperboloid of one sheet. There's two more left, okay? We're almost done. Hyperboloid of one sheet. Ellipses and hyperbolas. There it is. Hourglass. Kind of, to me, it looks like a nuclear reactor silo, kind of, a little bit. Okay, I won't go through the details of the cuts. Let's just look at the equation. There's your equation. All three variables are squared. They're all on the same side. Subtraction in one of them and equals 1. And then they can open up different directions, which I won't go through. Last one, hyperboloid of two sheets. So this is basically the picture we just saw. It just gets ripped apart. Like that silo that we had, that nuclear silo, we just kind of pull it to the point where it snaps in the middle, and then the two pieces come together, and you get these two bowls. So this is a surface. Kind of weird that that's a surface, huh? What is the equation of that? All three variables appear. All three of them are squared. Two of them are negative, and the whole thing is equal to 1. So you got to have two of them negative, and all three there, and all three squared. And then it can open up in different directions. All right. We have 7 minutes. Let's see if we can do this one. Given x squared equals 2y squared plus 3z squared, reduce it into its standard form and classify the surface. All right, so x squared equals 2y squared plus 3z squared. Anything you want to rule out right away? Does anybody have the textbook with them? Yeah. Okay. I would like for you to open up to a page, because there is a page that has a summary of all these. If you have your book. If you don't, then, you know, just know that this is here. This is 10.6. Page 578 has a nice little table with a summary of these different objects. So if I'm looking at this table, if I were looking at this equation, I would say, look, all three variables are squared here. And I can throw out some things then. I can throw out elliptic paraboloid, because that has a variable that's not squared. I can throw out a hyperbolic paraboloid. And that's about it. Okay, but I can eliminate some things. What happens if I try and get all my variables to one side? Or, you know what? Yeah.
Because it's one is on one side, two on the other side of the square, so it's a cone pattern.
Cone, so the cone would have variable on squared variables, two of them on one side, the other side just a squared variable.
With the cone, since it's like divided by the constants, so would that just be like for C, for example, would it be like 1 over the square root of 3?
Yes, we're going to change that. Let me put it up here so I don't have to go back on the slide. Here's a general form of a cone. Okay? That's a general form of a cone, which that looks a lot like, doesn't it? The way we can get it to look like this exactly is to get these 2 and this 3 out of here. And a clever way to do that would be to rewrite this as y squared over a half plus z squared over 1/3, like that. That's the same thing, right? And then you could now write this as x squared equals y squared over, and this is where you could rewrite that something squared, right? So 1 over root 2 squared plus z squared over 1 over root 3 squared. And that right there would be enough for you to be able to classify this as a cone. I mean, you could have, by just looking at it, knowing you would get to this, but that right there kind of illustrates that it looks like this. Now, we've switched the place of some of the variables, right? Like, this is z squared equals the other 2 squared and added, but that just means our cone opens in a different direction, right? It's not up and down. Instead, it's what? It's coming out the x-axis at us. Does that seem pretty okay? All right. How about this one? So you've got one variable. Any of them that have all 3 variables squared, you can throw out. So I'm looking at, let's see here. I have a formula here. I'm just going to jot it down up here. It's z over c equals x squared over a squared minus y squared over b squared. And this is actually a hyperbolic paraboloid. I'm going to put paraboloid. Hyperbolic paraboloid. Now let's see, does it fit into that? Can you get it to look something like this? Well, you have one of the variables has to be isolated and it's not squared. So that would be the 4x, right? So let's isolate this. So let's go 4x equals, and then I'll move things to the other side. How about y squared minus 3z squared? That looks a lot like this, doesn't it? Variable over constant, other variable squared minus other variable squared. So we've got, this is looking like it. I just need to make the fractions now. So how about make this x over what? 1/4 equals y squared over 1 squared. Right, that would match that. Minus z squared over 1 over root 3 squared. That looks like that, right? So we know it's a hyperbolic paraboloid. The only difference is that it's going to open up a different way than this standard one. All I really want you to be able to do is identify what it is, all right, like the name of it. Let's see if there's anything else here. I'm out of time. Did everybody sign in?
I got a question on that.
Yes, on the one we just did.
So, could it be an elliptic paraboloid if, let's say, we move the y squared over to the other side of the side, and makes it, top of y squared?
The format we have to have is that the squares have to be on the same side. So if you look at elliptic paraboloid, notice the squares are on the same side. There's addition between them. You won't be able to make that happen over there. Okay? All right, the last one here, just so you know, I'm not going to have time to do it. But the last one here, if you try and do this right now, it's not going to happen. Okay? Like, you're not going to be able to get it to match up. You actually have to complete the square first. So you have to get out, like we did this when we were finding spheres, centers of spheres. You have to put the x squared with the minus 2x, minus y squared with the 2y, the z squared minus 4z with the 4z, complete the square. Once you complete the square, then you'll be able to go match it up with something. That's a bit of a challenge there. Let's see how you do on that. At least I'm telling you, right? That's the homework for that section. We're done with 10.6. Anyone else need to sign in? Yeah. Okay. We're signing in for both Monday and Wednesday. All right? You'll have a good day. Good weekend, right? Good weekend if I don't see you before?